All right, we're going to go ahead and get started. I want to welcome you to the final presentations for Los Alamos Labs, for our Aggies events, that has been sponsored and hosted by Los Alamos Labs. My name is Rodney Boehm. I'm responsible for engineering entrepreneurship, and we have the pleasure of working with the student teams throughout the entire weekend. We also have had the immense pleasure of working with a number of absolutely fantastic mentors. So our students have told us over and over again in these kinds of events that the mentor interaction is the part that they enjoy the most. And so we really appreciate all of our mentors and everybody that's been engaged with us throughout the entire weekend. It's been a fantastic event, and we have really enjoyed working with them. What we're going to be doing now is we're going to be seeing the final presentations from each of the student teams. The teams will be presenting in order, and it'll start, and each team will be given 10 minutes. I will be timing them, and at the end of 10 minutes, I will stop everybody unless you've stopped earlier, all right? So you have 10 minutes to present your presentation. And then at the end of 10 minutes, I'm going to allow question and answer period. Now here's how this is going to happen. As each team gets ready to present, we will promote you to a panelist. Please keep your video and audio off until you get ready to present. If you want to, the person presenting can turn on their video, but the reason that we want this is so that the majority of your presentation is shown live on screen. We will be controlling your presentation, as we have said before, from here, and just tell us when you want us to go to the next slide. When it becomes time for the question and answers, then we're going to ask you to turn, the whole team to turn on your video, and we'll ask the judges to turn on their videos and audio as well. That way the judges will have 5 minutes to ask the teams questions. After your presentation and after you have finished, then what we'll do is we will then put you back in the panelist portion of the webinar, and we'll ask everybody to turn off their videos again, and we'll get ready for the next team. We're going to give the judges just a couple of minutes to finish entering their judging, and that's the way we're going to be able to put things together. All right? So what we are going to then put things together is, we'll get started here in just a couple of seconds. But before I do that, I'd like to ask the judges to turn on their video and to introduce themselves, because we have a tremendous panel of judges here, and we'll get a chance to hear from them, whichever one wants to start. All right, so I'm gonna actually call on you because Amy, I can see you first. So Amy, why don't you take it away and introduce yourself to the students and to us. And again, thank you, judges, so much for being here.
Hi, everybody. Thanks for having me today. I'm very excited to be seeing all of the projects that you all have been working on. My name's Amy Askin. My background is in civil engineering, and I'm from Lawrence Livermore National Laboratory, where I'm the associate program leader for radiological security. We work with domestic and international partners to secure their radioactive materials. I look forward to seeing all your presentations. Thank you.
All right, Diane, how about you? You're next up on my screen.
Hi, I'm Diane Hurtado. I actually work for the Texas A&M University System. I'm Associate Vice Chancellor for National Laboratories Management, and I got all 3 of my degrees from Texas A&M, and I'm an aerospace engineer. So.
Way to go. Great, Diane. Duncan, how about you next?
Hi, everyone. This is Duncan McBranch. I run a program at Los Alamos called Entrepreneurship for Mission Innovation. This is my second Aggies event as a judge, and I've been mentoring over the weekend, so I've gotten to interact with some of the teams. So really looking forward to the final presentations. Thank you.
Thank you, Duncan. All right, Edgar, you're up next.
Hi, my name is Edgar DiGiovanni. I'm a nuclear engineer at Lawrence Livermore National Lab. I have a background in chemical engineering and nuclear engineering, and I work in the Global Security Directorate, working as an analyst on fuel cycle issues.
Outstanding. Thanks. Don Quintana, you're up next.
Hello, everyone. I'm Don Quintana. It's my second time here at Aggie Invent. I'm glad to be here. I'm from Los Alamos. My specialty is thermal sciences with fluid mechanics and heat transfer. I'm a mechanical engineer. We really value this partnership with Texas A&M, and we're just so excited to see the work you're going to present today.
Okay, thanks, Don. All right, Amanda, you're up.
Hello, my name is Amanda Hammer. I'm the Senior Counterintelligence Officer at Pantex, so kind of an oddball on this, and this is my first event like this, but really excited to hear what you guys are working on.
Thanks, Amanda. We're all oddballs in some respects, I swear. All right, and Chuck, you're the next.
Hi, I'm Chuck Farrar. I am at Los Alamos National Laboratory. I lead an engineering institute there, which is a research and education collaboration between the lab and the University of California at San Diego. So we do a lot of education programs, and it's amazingly coincidental that Amy Askin was in one of those education programs a while back, and I haven't seen her in a long time. So
15 years
good
ago.
to see you again, Amy.
You know, and that's one of the interesting things about these virtual events. Sometimes we get a chance to see and make connections that we haven't seen before. So I'm really happy to see that. All right. Well, what we're going to do now is we're going to transition into the presentations, and we will be promoting the student team to panelists, and that gives them the ability to present as well as to turn their videos on. And judges, if you wouldn't mind turning your videos off, so that we can see the student presentations. And if you don't mind also muting, and that way we might be able to put things together. I'm getting the hi sign that I need to pause for just a few minutes, and we've got some making sure that we have everything set up, because we want the students to be able to present as efficiently and professionally as possible. We've been working on this as well. While I'm waiting, let me tell you just a couple of minutes to talk about their the engineering entrepreneurship program at Texas A&M University. This program is hosting the Aggies event. We're also sponsored and powered by the Student Engineers Council. The Student Engineers Council has provided some additional funding to engineering entrepreneurship because they think so highly of the program. And so Aggies event has been named as being powered by the Student Engineers Council. Engineering entrepreneurship gives you the opportunity to provide some entrepreneurial mindset along with your engineering degree. And that engineering degree is a highly and a great technical degree. You're going to get one of the best technical degrees that you can at Texas A&M University. We're going to augment that with some skills that allow you to be even more effective as an employee, because we're going to help you understand that when you design something, there's a customer behind it, and provide you with entrepreneur skills, as well as the ability to spend some time putting together effective communication. So this is a program that we not only provide as an education through curricular, but extracurricular activities. And the extracurricular activities that we have is one of them, and the signature one is Aggies event that we've been working on now. I'm going to pause for just a second, and now I believe that we are ready. And so the first team is Sixth Sense, and I'm going to mute and stop my video. And Sixth Sense will be sharing the screen, and you'll be ready to take off as soon as we share the presentation and ready for you to go. All right, Sixth Sense, you're ready.
Howdy, we are Team Sixth Sense, and we are creating a safer workplace. My name is Mary Ellen Crow. I'm a freshman. I'm a general engineering major.
Howdy, I'm Emily Carrizales. I'm a junior and I'm an electronic system major.
Howdy, I'm Catherine Leach, and I'm a freshman biomedical engineering major. And I think we're waiting on one of our teammates to be promoted right now. He was labeled as Corrosion Cowboys, but I think he's actually, he's with us. Kamran.
Okay, who is it needs to be promoted?
Kamran, I'm not sure how to pronounce his last name.
Darvish.
Yes.
Darvish.
Kamran Darvish.
Okay.
And maybe we should start over once we get him promoted.
I agree.
I think he typed in his name, Corrosion Cowboys, Darvish.
Okay. Let's get started. Let's go back to the very beginning and let's start over again.
Howdy, we are Team Sixth Sense, and we are creating a safer workplace. My name is Mary Ellen Crow. I'm a freshman, and I'm a general engineering major.
Howdy, I'm Emily Carrizales. I'm a junior and I'm an electronic systems major.
Howdy, my name is Kamran Darvish, and I'm a senior biomedical engineering major.
Howdy, my name is Catherine Leach, and I'm a freshman biomedical engineering major.
Howdy, my name is An. I'm a junior and I'm a nuclear engineering major.
Howdy, my name is Margaret. I am a freshman general engineering major. And please enjoy the video that we have prepared for you guys.
Would you wait a day to find out you've been poisoned? A week? A month? How about 3? No, of course not. However, that's a risk many workers in radiation-related occupations take every day. Radiation is a serious and invisible threat. Exposure to radiation damages cells, interferes with the body's normal functioning, and can lead to serious health complications, such as cancer. Personal dosimeters workers wear are commonly only submitted for testing once every quarter. This opens the door for accidental radiation exposure to go unnoticed. That period of time can create serious health concerns. What if there was a way to detect real-time, personalized radiation absorbances? Introducing Sixth Sense. Sixth Sense combines modern e-textile technology and real-time radiation sensors to create a practical solution to radiation detection. Workers wear a wireless circuit which lights up once a dangerous amount of radiation is absorbed in any given minute. The versatile e-textile sensor system can be easily integrated into clothing regularly worn at each job site. Sixth Sense creates safer work environments, allowing workers to feel more confident. This results in greater innovation and the discovery of solutions to make the world a better place.
So as seen in the video, we are Sixth Sense and we are fulfilling the need for individualized real-time radiation detection in style. When we began researching this concept, we discovered that currently the device most commonly used to track employee radiation exposure are thermoluminescent dosimeters, which unfortunately they require elevated temperatures and laboratory conditions to retrieve their data, meaning that there's an opportunity that accidental exposure could go unnoticed for as long as 3 months. An individualized real-time radiation detector would help ensure that ALARA standards were strictly kept, and it would provide a quick, efficient, and immediate response in an emergency situation. Not only would the health of the employee benefit from such a device, but also the health of the business, as confidence in personal exposure data results in lower healthcare costs, as well as it mitigates project risks by keeping employees in the workplace instead of having to stay home due to reaching their exposure caps. Finally, this device would also boost company morale due to the feeling of increased security, which increases innovation, which leads to the discovery of solutions to the world's greatest problems. Now, my teammate Margaret is going to discuss some of the requirements we considered when going into this problem.
Could I have the next slide, please? So there are the four requirements that we considered when pushing for our product was immediate feedback, the fact that it has to be comfortable to wear, accurate data, and cost efficiency. So when talking about a wearable clothing item, it has to be comfortable because we want to be able to allow detection without taking away mobility. And we understand that it's already really uncomfortable with all the layers of protection that it has to be worn. So our proposition has no more than 1/2 added pound to a normal lab coat weight, which my teammate On will show the prototype later. And when talking about accuracy, we want to pinpoint the sensitive organs on the body. So that means that there will be sensors located at the lung, heart, and kidney, as well as other reproductive organs to alert the user if that area has been affected. And next On will go over the prototype of the actual lab coat.
So our design, it incorporates existing radiation sensors with e-textiles in an everyday lab coat. The prototype features radiation sensors that are connected through a circuit to the LEDs and e-textiles that are woven into the lab coat. This system is powered by a battery connected to the back pocket of the lab coat. These sensors, they can detect alpha, beta, gamma, and X-ray radiation and are continuously recording the energy input data in real time in minute intervals and monitoring for a certain energy threshold. That energy threshold was calculated at an approximate 3.9 microrem per minute. Once that threshold is reached, the sensor triggers the e-textile and the LEDs to light up, signaling to the worker that they have been exposed to a high dosage, high dosage level, and that they should leave the area immediately and follow their emergency protocol. Now, here's Emily with some more details on the components in the next slide.
E-textiles are fabrics weaved from normal threads and conductive threads. Circuits and light strips can be printed onto this material and will require batteries. Sensors and additional lights can be embedded onto the fabric, creating an electric system that's wireless and washable.
The sensors, which are developed by First Sensor of TE connectivity, have features such as reading in very low dark current signals, low capacitance levels, and minimal series resistance at full depletion. The sensors have an active area size of 10 millimeters squared, and also custom specific options, including thicker silicones and fully depletable chip designs, are also available upon request.
These sensors can be embedded into the circuit, and the signals will be sent to our central hub that has a battery and a general processor. Kamran will explain about the dosimeters and how our solution can be a potential upgrade.
Next slide, please. Our device monitors the rate of radiation absorption. However, we are also proposing a new mechanism to store these radiation dosage values in our device. Then we can upload those radiation dosage values to the memory of a computer. And what this allows us to do is maintain continual and cumulative radiation dosages for each employee who uses our device. So essentially, there is no need for a dosimeter anymore because we are achieving cumulative exposure levels for each employee, which is a function of a dosimeter. Now, employees do not have to worry about keeping a dosimeter on them everywhere they go, or perhaps forgetting it, because it will simply be on their lab coat. So we do consider our device an innovation in this regard. Now, Mary Ellen is going to tell you about the future directions that we plan to take this device. Next slide, please.
So some future directions that we're looking into for our product would be adding an auditory alert along with the lights to better notify the user in case of an emergency. We would also like to include a tracking system in the device to pinpoint where within the building there is radiation exposure so that other employees can be notified and the source can be contained. And finally, we would like to create other garments such as gloves or vests for those working in the medical field, like X-ray technicians or uranium miners who could possibly be exposed to radiation at any point in their daily work. Our product could save countless lives and give workers a stronger sense of safety and security. And on our next slide, we'll have a bibliography of our research.
On behalf of Team 6 Sense, thank you for your time. And now we open the floor to any questions.
Thank you very much. And judges, if you'll turn on your video, and Sixth Sense, if y'all will all turn on your video and your audio so that you can respond to questions, we would appreciate it. And judges, you have 5 minutes for questions.
My video's not allowing, it says host has stopped it.
Okay. Thank you.
Bobby,
I'll
I've
check.
got a question.
Yes.
This is Duncan. So team, say a little bit more about the sensors and then the cost of the system. I didn't hear the cost that was addressed as part of the presentation.
Thank you so much for your question. Don, if you don't mind going to the slide after questions, please. We actually have some information about the pricing. We anticipate the pricing to be around $750 per coat. And that's just because of the 3 sensors and the e-textiles, which must be purchased along with labor. However, we do anticipate lots of costs to be saved. And these costs include emergency radiation maintenance because our device mitigates that. This also involves prices that are associated with workers being unable to come in due to yearly exposure already being reached, which is extremely expensive. And finally, worker confidence is something that we believe is immeasurable.
This is Edgar. I have a question. So why the choice of 3 sensors when typical rad workers are wearing 1 sensor during their work for most situations?
I'll answer that question. So what we decided to do was we wanted to pinpoint specific areas on the body that could be more prone to the effects of radiation. So those would be the sensitive organs, such as the lungs, kidney, heart. So with that being said, we thought that would be a priority in having multiple areas just so we could specify where the effect was taking place.
Thank you.
Did you consider any other options as you were coming up with this prototype idea?
I'll answer that one too, unless anyone else wants to jump in. Yes, we did have many alternate designs, but ultimately we just thought it would be best to have something that could end up being really versatile. So like Mary Ellen mentioned in our future applications, we could put sensors and integrate in the textile fabric onto gloves, watches, wristbands. It could potentially be for any garment. So lab coat was just something that is really general and broadly used. So we thought that would be a good place to start.
Yes, one of our first designs, we thought about making the entire coat out of e-textiles, but then not only did we realize that would be very expensive, it was also, it decreased like you'd have to manufacture specifically only lab coats. By isolating the system into just strips of e-textiles to the sensors and then to the general processor, that could be used in multiple, it could be used in a vest, in gloves, in a wide variety of clothing.
Also reduce costs drastically if we just have strips.
Okay, I'll ask one. So could you talk a little bit more about the actual transducer, what takes the radiation environment and converts it into an electrical signal?
Yes, definitely. So basically, we have found radiation sensors on the market, which we believe are very new. But we hope to incorporate a sort of electrical circuit within the lab coat. And what enables us to do this is it's extremely wireless, and that's because we have e-textiles that are cloth that are able to conduct electricity. So we hope to generate from the sensor, the radiation sensor, we hope to able to basically adjust the circuit in such a way that the lighting mechanism is lit up once a certain threshold of rate of radiation is reached by the sensors.
Okay, thank you.
I have a question. Can you talk a little bit about like maintenance, washing, calibration, that kind of thing?
And this is the last question.
Yes, absolutely. Don, if you wouldn't mind going to the slide after the pricing, please. We anticipate some washing questions. Basically, we have a proposed mechanism of sterilization, which is UV light. But one of the future directions that we want to take is to make the entire lab coat washable. And this can be achieved by laminating the e-textiles and covering the sensors.
Okay, thank you very much. 6th Sense. Sorry for the slight detail or issue during the video, but we corrected it and made sure that you had plenty of time to take care of it. Thank you very much. If y'all will now turn off your videos, and panelists and judges, if y'all will turn off your videos as well, we'll get ready for the next team, which is TKO Nukes. And as we are getting ready for the next team, we will promote the team members from TKO Nukes to panelists, and that will allow them to turn on your video at the appropriate time. We'll also get your presentation up and ready. So let me continue on with talking about the engineering entrepreneurship. We also have a program in engineering entrepreneurship that is called an engineering incubator. We call it Engineering Inc. And it's an incubator that allows you to continue on with your ideas and turn them into startup companies or continue to work with other people who are interested in turning and taking their ideas to the next level. We'll provide you space. We'll also provide you with a little bit of funding, but more importantly, we'll provide you with the guidance and the mentorship to help you figure out how to take your idea to the next level. We want to make sure that all of the teams and the Aggies Invent teams know that this opportunity is available to you. So you have that opportunity to not only spend some time this weekend on your idea, but if you as a team are ready to take it to the next level, then we encourage you and will work with you to continue on and take it on and maybe even turn it into the next startup. We just had a team that will be launching in the next few days that is out of Engineering Inc. We have 21 other teams that are continuing to work on that program. And Professor Jim Donnell is the primary lead of that particular program. And as many of you know, you worked with him this weekend, and he's a tremendous asset at being able to put all these things together. So again, not only do you have curricular, but you have extracurricular activities available to you at Engineering Inc. And we do hope that you take advantage of them at all times. All right, we are ready for the next team, which is TKO Nukes, and we'll be hearing from them. So whenever we get your screen up and ready, then you can get started and we will listen to your presentation. Thank you very much.
Hi everyone, we are TKO Nukes, and today we're going to be talking to you about detecting nuclear blasts from space. Next slide, please. So this is our team. Let's go ahead and introduce ourselves.
My name is Carson Adams. I'm a general engineering major. I'm a freshman.
My name is Maidia Norve. I'm a senior nuclear engineering student.
My name is Justin Barnes. I'm a freshman engineering student.
I'm Carlo D'Aclido. I'm a freshman general engineering student.
I'm Rishi Fatak, and I'm a sophomore computer science major.
minutes. That's how long it takes an ICBM to travel halfway across the globe and decimate millions in the blink of an eye. The fact could not be understated further. Our world is in constant danger of a nuclear threat. The only chance we have is stopping it before it happens. The first and the most important step in preventing a disaster is detecting initial nuclear weapons tests.
The Vela satellites sent to solve this problem are now expired and surpass 300 pounds. Even worse is the Vela incident, where the signature double flash of a nuclear bomb occurred, but no sign of an explosion nor X-ray data was recorded. The uncertainty surrounding what caused the Vela incident proves the reliability of the Vela satellites was inconclusive for nuclear monitoring. Our design ensures no false positives and accurate readings with just 20 watts of power, 10 cubic inches of volume, and weighing no more than 50 pounds. The bang meter searches for a double flash of a bomb, while the gimbaled X-ray and microcontroller search for the source of the bomb's location. By using these sensors combined, the identification of a nuclear testing makes the world a safer place.
So this is just a brief overview of what we're going to be showing today in this presentation. Next slide, please. So onto the problem. So what exactly are we trying to solve here? Next slide, please. Well, in short, we're trying to prevent nuclear war, but what we're really trying to do more specifically is create a satellite-based detection system that picks up on X-rays from nuclear blasts and pinpoints the time and location of those X-rays. And the reason we're doing this is in order to detect nuclear weapons testing operations. Now, there's officially nuclear weapons tests are banned by numerous international treaties. but any country can just sign a piece of paper and then go behind the back of the international community and keep on doing nuclear weapons tests and putting the security of the world at risk. So with this technology, we'll be able to monitor compliance with these treaties and make sure these countries are being held to their word. Next slide, please.
Moving on, there are some limitations and constraints when designing our solution. The next slide. There's a constant need for satellites to be smaller, more energy efficient, and lighter. So we had some limitations when designing our solution. The first one was it was not to exceed 10 inches on each side, and it would need to be under 50 pounds. Our design would also consume less than 20 watts of power. Due to the extremes of space, it would need high temperature resistance and radiation protection. And the sensors would need to give accurate and reliable data. During launch, our solution would need to provide humidity and vibration resistance. Next slide.
Onto our concept and some possible solutions. Next slide, please. Our first idea for the X-ray detection was a photomultiplier tube. We found this solution to be too large for our volume constraints, and it was a relatively old technology. So we looked into a 2D X-ray sensor that took up much less volume and consumed much less power than the photomultiplier tube. The size of the solution meant we could attach it to a 3D gimbal system and be able to pinpoint exactly where on the Earth the X-rays were coming from. Next slide, please.
Pulling from the requirements we identified earlier, we compiled a list of either materials or objects that would rectify both problems and complications we could encounter, as well as following the specifications we needed to meet. Next slide, please.
Onto our solution. Next slide, please. As you can see in the top right, there's a bang meter peeking out of a lens, which looks actively to detect a double flash. And here we have an animation of the 3D gimbal system. And in the system, as you can see, it's constantly scanning outside of the lens for the X-rays that are coming from specific parts of the Earth in order to pinpoint exactly where it is on planet Earth. Next slide, please.
Now into some of the features of our technology. Next slide, please. So the first feature we have here is the two-dimensional scintillator technology. And how this works is basically when the X-ray radiation hits the scintillator, the iodide crystals in the scintillator are excited and they release photons. Those photons are picked up by the photoiodide array, which is housed right under the scintillator. And once the photons hit the iodide array, it releases an electrical impulse, and that's how we detect the X-ray radiation. Now, we wanted to make it two-dimensional in order to increase the surface area to volume ratio. You want as much surface area as possible so that we could detect radiation easily, but we want as little volume as possible so that we aren't using any unnecessary space. Next slide, please.
We also utilized a bang sensor, specifically a germanium photodiode, and we did this for the purpose of detecting the double flash that comes from a nuclear bomb, as can be seen on the right. And we did this to ensure no false positives. So by combining both the scintillator and the bang sensor, it makes our design more accurate and reliable. Next slide, please.
So the scintillator and the bang sensor are going to send an electrical signal to the onboard computers. And this is where the machine learning model is going to interpret the signal that's coming to it and send a log file out, as you can see on the bottom right here, out to ground. So the actual machine learning model is going to be pre-trained down on Earth using historical and artificially generated data. And the onboard computers are going to be radiation resistant. They're going to do this by having physical hardening and logical corrections. They're going to communicate the log file back to the main satellite using the spacewire system, which in turn is going to connect back to ground. Next slide, please.
Here's a broken down model of our design so we could see the individual components. In the center, we have our detector and our communications board, and all the electronics are coated with a silicone coating for the purpose of helping with radiation protection as well as humidity. And this coating also provides thermal control. And then you see the bolts in the front, the vented bolts help combat the vacuum environment of space. And the back bolts are threaded fasteners with a spiral lock, which help ensure the structural integrity during launch. And then around everything, we have an aluminum lithium casing to further protect from various forms of radiation while still maintaining the lightweight requirement. Next slide, please.
So on to our conclusion. What are the key takeaways that we can get from all of this? Next slide, please. So first of all, there are numerous international treaties preventing nuclear weapons testing, but without any way to monitor those treaties, we have no way to ensure that they're being followed. So we need to detect nuclear weapons in the testing phase so that the problem doesn't get out of hand and we can prevent disaster before it strikes. We also need to get past old methods to detect these nuclear blasts, such as the Vela satellites, because as we've seen from the Vela incident, there's a lot of uncertainty with these methods and they use a lot of outdated technology. We also are using double flash detection and X-ray scintillation because those are among the most powerful tools that we have to actually detect these nuclear blasts. Another thing to consider is that there are no do-overs with nuclear war. So that means we cannot have false positives. We need to ensure accuracy and reliability because the consequences if we aren't accurate are catastrophic. Next, the innovation in nuclear detection takes place through detectors becoming lighter, more compact, more energy efficient, and more precise. And finally, with this technology in place and these considerations in mind, we can help make the world safer for ourselves, our children, and our planet. Because nuclear detection prevents nuclear destruction. Thank you. Are there any questions?
Thank you very much. You hit it right on the money. So if everyone will turn on their video, judges, you have 5 minutes for questions.
I had a question. Did you do a power budget to ensure you weren't exceeding your 20-watt requirement?
When we looked into the budget, the biggest thing we found is that the servos, we calculated them at a max load of 1.8 watts. Everything else we had attempted to look at. I think the only power draw that significantly was going to affect anything was the scintillator, which we estimated is somewhere around 13 watts. And the only other draw we would have is from the bang meters. And so because the bang meters took up they can either take up no volt or no wattage at all and be ran in a passive, essentially a solar cell mode, or we can put an inverse voltage or reverse voltage through them in order to get more accurate readings. We decided to go ahead and do the reverse voltage as it was only 0.1 watts to put through it, but that would significantly help the amount of readings and the accuracy of the readings to the bang meter. So we initially had one bang meter, but we could replace it with even 3 or 4 bang meters to ensure that we get more reliability, and still all this would remain significantly under the 20 watts.
Okay, I hope I didn't miss this because I was doing some notes on the grade sheet, but what's the telemetry system that gets the information acquired by the sensor down to people who have to make a decision about what to do with the data that comes in? And does that have a big power requirement with it?
So our understanding of the problem was that our part of the model was going to be based on the outside of another satellite. So we based our model on the constraints that the 20 watts was going to be used by only our instruments. And so the SpaceWire system that I was talking about communicates to the main satellite, and the systems of the main satellite are then going to communicate the log file back down to ground.
Very good.
You said one of your innovations was that you had a 3D gimbal mount, and that was going to slew to track the signal. Is there a disconnect between the time it takes to slew that whole system versus the time that the signal is coming in, and can you actually do tracking that way?
So it is very possible for us to do the tracking between when the X-rays are emitted versus when it's actually received by the 3D gimbal system. One of the things we discussed as a team is that if the gimbal system is on one side of the Earth, but the X-rays are coming from the other side of the Earth, we would still see an abnormal amount of X-rays once it performs a scan. And using this kind of information, we could trace back when we started receiving the X-rays and what the likely original detection of the X-rays, where it would be, and the power of those X-rays. So a lot of it is based off of when an abnormal amount of X-rays are detected, what are the next steps for the gimbal? And that would be less of do just random scanning around the Earth and say like a circle format versus trying to pinpoint exactly where it's coming from. And a lot of this is cross-communicated with, say, what the bang meter detects. So if the bang meter for sure detects the double flash, which is very, very signature of a nuclear bomb, it's very likely that the gimbal system is going to go towards a different mode of detection as opposed to a random mode from being where is the most amount of X-rays coming from. So it's not going to say go left when it should be going right. And so these kind of methods, when put together, can help us really zoom in very quickly too on where the X-rays are coming from to get the most amount of data possible to identify the nuclear signature.
So
can you speak to the limits of your X-ray detection as far as energy levels or frequency?
So for the actual scintillator we chose, we had to make a decision between two scintillators of that size. One of them was a silicon scintillator, and the other one was some iodide form, a cesium iodide scintillator. And we eventually chose the silicon one because it had detected from 120 keV below, while the other one was only 100 Kelvin below. And even better yet is that the silicon one didn't have humidity issues, and so the cesium iodide one had issues with humidity, and because we wanted to avoid that and the fact that it couldn't be stored in humid environments, we decided to go ahead and go with the silicon one, even though that they were the same dimensional size. And so being able to choose which one specifically is good for the operation is kind of the decision we had to arrive. So we chose silicon.
So my understanding is there's other sources of X-rays in space other than nuclear detections. And do you have a strategy for separating gamma ray bursts from nuclear detonations?
So I know we did talk about the Vela incident, which was like supposedly people weren't able to tell it apart from a nuclear explosion. But the chances that two back-to-back flashes will be a natural event rather than a nuclear event are exponentially unlikely. And also the model that we're going to train should be able to hopefully differentiate between these kinds of events.
Very good.
Okay, TKO Nukes, unfortunately, that's the amount of time. That's 5 minutes. So I appreciate all of the time and all the questions. I see you got a tremendous amount of questions, and great job with your presentation. So thank you very much, TKO Nukes. And we look forward to hearing more from you a bit later. As we get ready for the next group, which will be Corrosion Cowboys, we'll ask the judges to again turn off their video and then do the scoring. And that way we have an opportunity to get ready. As we're talking about this, I'm going to also spend a couple of minutes just talking about some of the courses that we have coming up. Corrosion Cowboys is going to be a very interesting presentation because they're going to be talking about how to avoid and detect corrosion on certain elements. And they'll get into that detail, but they've done a great deal of research, as have all of the teams throughout the entire weekend. Now, the courses that we're talking about that will be taught next spring, there's a number of them. Some of them are lean startup classes. In other words, helps you to take things that go off and launch a startup. Now, those are going to be the engineering courses of product lean startup, and there's also one focused on defense problems that's called Innovate for Defense. The other class that you might be interested in is an enterprise basics class, and this is a class that's taught by Professor Donnell. Oh, by the way, I teach the two lean startup classes, and then Professor Donnell will be teaching the enterprise basics class. All right, I'll cover a little bit more about some of the other courses in the next break between the teams, But just to remind you that these courses and a flyer for these courses is posted in the general channel and Teams environment. We do hope to see you in these courses, and we hope to be able to help you continue your education and continue development of an entrepreneurial mindset. All right, we'll get ready for Corrosion Cowboys. I think we're ready to go. And Corrosion Cowboys, as soon as your screen is shared and up ready to go, you're more than welcome to take it away.
Howdy, we're the Corrosion Cowboys, and my name is Kirthval Ramesh. The other team members are Shriyabi Venkit, Megan Novak, Quinn Burke, and Arthur Provo Bose. We are all freshmen. 3 of us are computer science majors. Megan is a chemical engineering major, and Quinn is an aerospace engineering major. Can I get the next slide, please? So our problem statement is increasing the lifespan of satellites by early detection of corrosion. Next slide, please. The first thing is our need statement, where we're developing a non-intrusive corrosion detection. Sorry, the thing's in the way. That can detect the size, location, and type of corrosion within satellite or other aerospace assemblies. Next slide, please.
A few of the requirements that we took into consideration are listed here. So the first one that we looked into was non-intrusive, for our product to be non-intrusive. We realized that we did not want to mess with an already functioning piece of technology, which would be in this case the satellite. So that rather we focused on adding another layer on top of it so that we could improve upon it. The next thing we looked at was the location of we wanted to be able to detect the location of the corrosion, because if we have the location of the corrosion, we can easily go and either repair it or we can prevent it from spreading across the rest of the satellite. The third thing we looked into was the classification of the corrosion. So we recently learned that there are many types of different corrosion, and that being able to classify them was a big part of being able to repair and being able to prevent them from spreading. So one more requirement that we looked into was long-term stability. Since corrosion happens over a long period of time, we figured that the only way to make our product very long-term stable was for it to be able to last a long time in space. And in order to do that, one thing that we really focused on was for it to be immune to the corrosion itself. And then the last thing was since our main target for this product was satellites in space, we realized that it would be impossible to operate it on a regular basis without a remote connection or something like that. So those were the main requirements that we took into consideration. Next slide, please.
So the first design alternatives we were looking at was the eddy current detection method. The way this works is that you pulse a magnetic field near a metal object like a pipe, and then that magnetic field induces an electric field inside of the pipe, and you read the output of that electric field to see the deviation from what a normal pipe would look like, and from that you can figure out what the corrosion looks like in that pipe.
Thanks, Quinn. You guys have heard about the eddy currents. Now let me tell you about ultrasound that we explored. We were planning on bouncing ultrasound rays through the metal objects we were trying to detect and get an ultrasound report. The only problem with this is that ultrasounds are very famously grainy and that we may not be able to get an accurate report. So if we're going to put a lot of money into this, we want the best value of this out of this. So it's not feasible. The last way we thought about this was having a camera monitor corrosion through convolutional methods. So basically, we take a picture of various pipes around the spaceship, and we try to feed this through a convolutional neural network, and it would predict what type of corrosion it is and what the size is. This, the only problem with this is that we can't take pictures of within the pipes, which is where corrosion would be, would have the most corrosion. Is there simply a better way? Now I'm going to hand it off to Megan to talk a little bit about the research aspect of her presentation. Next slide, please.
The research we did allowed us to discover what types of issues were plaguing spacecraft and the different types of corrosion. And we learned that the same oxygen that keeps us alive on Earth is destroying our satellites in space. Atomic oxygen is the #1 cause of corrosion in space, and it causes many different types of destructive manners to the outside of spacecrafts. We also decided on electric currents as our method to look at corrosion because it is non-intrusive and can be placed at different places to avoid damage to sensitive electronics. Can we have the next slide, please? There are different forms of corrosion, and we'll go into further detail about how we're going to classify each one of these. There's electrochemical corrosion, which forms an oxide layer. There's stress corrosion, cracking. And there's also pit and wall loss. And the figure below shows the centralized corrosion, then the generalized corrosion and localized corrosion. And our detection systems can pick up on both of these. We also looked into various materials that are more susceptible to corrosion, which include silver and iron and polymers with fluorine in them and can corrode with long-term exposure to UV. Next slide, please.
Okay, before I get too far into it, I want to warn that I'm going to do a lot of talking about pipes. And this method doesn't only work on pipes, it can work on any metal piece you can run a current through, but the pipe example is really easy to understand. I should also warn Don I'm going to go through these slides kind of fast. So next slide, please. On the left is a cross-section of a pipe, and on the right is the cross-section of the same pipe after it's suffered some corrosion, excuse me. Next slide, please. As you can see, the pipe loses some area as it corrodes. Next slide, please. And the resistance of a pipe, or any metal object really, is based on rho, which is determined by the material times the length over the area. Next slide, please. And so since the areas are different, that means the resistance values of the pipe before it's corroded and after it's corroded are different. Next slide, please. And so the way we're going to leverage that into determining something useful is we pick 2 points on the pipe that are some distance apart and we run a current through the pipe. Next slide, please. Between those 2 points, we run a voltmeter, and this helps us determine the resistance based on the current and the voltage between them, which will give us the resistance. And the change in the resistance is the same as the change in area. Next slide, please. Not it's the same, excuse me, but it's related. And so you can figure out how much the pipe has lost based on the change in the resistance. And so if you have the measurement from before you started corroding and after you started corroding, you can tell how much metal you've lost almost exactly. And with this method, you can also form maps. Next slide, please. So here is an example of a more advanced mockup that has a lot of electrodes, and the electrodes are connected back to a controller so that you can take a more detailed image. Next slide, please. And here's an example of some of the imaging that you can do with this method. In the top left is a graph of metal loss on the left versus time on the bottom, and you can see that you slowly lose metal over time. To the right of that image is a 3D map almost of where the metal is corroding in a pipe. And on the bottom is a map of where you can see how you could see pitting versus wall loss with this method. You can see that in certain areas you can see a localized big gap where the regular pipe has only lost a certain amount. That one area has lost a much larger amount, and that helps you detect pitting. And now for the next slide about the machine learning applications.
Thanks, Quinn. Now let's dive in a little into the defining feature of our plan, machine learning. So how can machine learning work with detecting corrosion? So an intelligent system needs data. We provide that for our neural network with a four-dimensional data set. Temperature, whether it's facing the sun, the substance types entering the pipes, and the UV radiation, which is also a binary data value. Next slide, please. So our intelligent system predicts and classifies. we will be feeding these 4 data inputs into our neural network, as you can see in this diagram. So you're going to have 4 of these inputs here, and you're going to have an n amount of hidden layers to increase accuracy. Now, if you saw in the prototype with Quinn, you saw that there were multiple pins. For simplicity's sake, we've only put 4 output neurons, but in the actual neural network, we would actually have an output layer of 48 neurons. So this model basically just says that you could show that like which of the pins has the highest probability of corroding and which type of corrosion is based on a simple clustering algorithm that extrapolates data. Now I'll hand the floor off to Kirti, who will close us off by talking about the innovation of our product. Next slide, please.
Hi, so I want to talk a little bit more about machine learning here. So we use predictive modeling to turn off our system when it's not needed. So for examples, in lower temperature, there's a much lower risk of corrosion. So our model could simply turn off the system, and there's several advantages to this. The first is that it saves energy for
Corrosion
systems on a
Cowboys,
satellite that need it the most.
Excuse me, that's
it
been
reduces
Corrosion Cowboys. That's been 10 minutes. And so thank you very much. And it's time for questions. If judges, if y'all will come on and everybody come on, and it gives you an opportunity to ask questions. And you have 5 minutes for questions, judges.
I've got one. You spent a lot of time talking about the pipe, which is understandable and simple. How do you extend from a pipe to a spacecraft in terms of pinpointing type and location of corrosion?
So the method works on any type of metal object you can run a current through. We've just used the pipe method because this technique for imaging corrosion was developed for usually refineries, so it's used in pipelines, and I use that example because it had the best documentation. And so anything that you could run a current through, you could theoretically use the same method on and be able to figure out the corrosion.
So in the description of your machine learning, you had several parameters that looked like they were specific to pipes. Like I think if I saw that right, whatever material was in the pipe was one of the parameters that would be part of the algorithm. So again, how does that translate then to other types of structural components?
A 4-dimensional data set would be the most ideal situation here. Obviously, some places pipe actually will not work. So we'll have to have a 3-dimensional data set, which will provide a less accuracy, but as we increase our data set over time, we'll still end up with that low error when we fit our data.
So how might your solution affect the other sort of performance components of those aerospace components in terms of like weight and other issues that might be required to implement the solution on an aerospace kind of application?
The actual thing itself shouldn't weigh very much, and the volume isn't very much. From the commercial models that are available right now, the size and the weight is almost entirely put into components that are not necessary in this application, like solar panels and wireless transmitters, because they're used in remote locations. But this will be embedded into spacecraft, so we will have a relatively lightweight because all we need is the electrodes and a controller for them.
The other thing to note with that is that our product solely relies on changing or calculating the change in resistance. So we don't need a lot of power to run this either, because we only need enough to register the amount of resistance change.
Did your model, you probably got cut off early, but it sounded like you had some discrete points for prediction, like temperature and exposure, but did you also have some other prediction tools, analytical tools incorporated in there for adapting?
So basically, this is only like one type of situation. So we can only predict and classify corrosion, right? And we can't really like do anything else with that. Like we can, based on the parameters we're given, we have like a lot of readily available data that we can provide for. So if we want the most accurate result from our model, we can only use these 4 because we explored other ways to get data that may be more flexible and more adaptive, but we quickly realized that it wouldn't actually give us the most accurate result. So
what would you say is your biggest source of uncertainty or variability in your prediction process?
the variability can range from anything from honestly radiation to like the substances flowing through, or just the like uniform current. Like in some situations, we may not even have uniform current passing through. So there are many factors that we can take into like consideration that may bias our model, right? Because in the end, it may be an intelligent system, but in the end, it is simply an algorithm.
Okay, there's time for one more question.
What are the current levels that are being pulsed through this?
To be absolutely truthful with you, I couldn't tell you that off the top of my head, but this is a commercial technology that you can buy. And so this is developed enough that this is not information that is like groundbreaking. This is known.
Right. It's just that we implement it into the spacecraft, satellites in a way that we think would be really, really useful to detect corrosion.
All right. Thank you very much, Corrosion Cowboys. Really appreciate your presentation and appreciate the information. Judges, again, I'll give you a few minutes to complete the judging and the scoring and submit the scores when you have an opportunity as we get ready for the next team, which will be WRD. As we were talking before, the courses that we'll be offering are 3 courses that are for engineering entrepreneurship. There's also 3 other courses that are going to be offered. And one of them is taught by Dr. Cynthia Hopewell, and Chris Sears. It is on agile technology and leadership. And this is this will be a great course to learn more about agile leadership. And then the next course will be entrepreneurship and nano and energy systems, where you'll be analyzing and learning more about nanotechnologies and how they put together. And those 2 courses are available to anyone. The final course is a petroleum engineering course that, again, Professor Jim Donnell will be providing, as well as co-teaching. It's available for petroleum engineers, where they not only build a business plan, but you'll also be taking a look at sizing of reservoirs and understanding the business associated with petroleum engineering. So those are courses that are available from engineering entrepreneurship, as well as mechanical engineering and courses that you might be interested in. All of those courses count for the concept creation and commercialization certificate that will be offered by engineering entrepreneurship. We will be putting together and getting ready to go with WRD, and I have the sign that everything is ready. So WRD, when you see your slides start, you're more than welcome to get started, and you'll have 10 minutes to complete your presentation with 5 minutes of questions afterwards.
Hello, ladies and gentlemen. Thank you for joining us on this wonderful afternoon. We are WRD, which stands for Wearable Radiation Detection. Next slide, please. So I'm going to go ahead and give our members a chance to introduce themselves.
Hi. Sorry. Hi, I'm Megan Ellis. I'm a biology major and I'm from class of 2024.
Hello, I'm Emiliano Contreras. I'm a mechanical engineering major from class of 2024.
Howdy, my name is Evelyn Wendt. I'm an aerospace engineering major, class of 2023.
Hi everybody, I'm Isabel Grimacy and I'm a computer science major, class of 2024.
Next slide, please.
Cancer, organ failure, radiation poisoning, and autoimmune diseases are all serious medical conditions that can result from exposure to high levels of ionizing radiation. These illnesses can cause a lifetime of harm to patients, and the effects of those illnesses are felt by all of those around them. Thus, when workers are potentially exposed to high levels of radiation every day at their work, it's important they can stay safe and understand their risk. To help keep those workers safe and informed, we've developed the WRD. The WRD is a system that can be easily integrated into any workspace but brings safety and reassurance to radioactive material handlers. The system works using a series of radiation detecting sensors that's built into equipment workers already use every day. The unique detecting system uses a network of fiber optic cables and radiation sensors to pinpoint the intensity and the location of radiation on the coat. For workers, it's as simple as donning their lab coat, vest, or ESD and plugging in their WRD screen. When workers are exposed to potentially harmful radiation, they're alerted with a buzz, an alarm, and they're able to view the intensity, location, and danger level of the radiation they are being exposed to. The WRD helps bring safety and confidence into workspaces, so the second there's exposure to radiation, you're informed and able to act. Protecting handlers of radioactive materials is now easier, faster, and more informative than ever.
All right, so our problem statement was we all know that workers and researchers handling radioactive material do have a risk of getting exposed to this radioactive material, and we need to be able to allow them to quickly and accurately detect this harmful radiation in case of a exposure. Next slide, please. So currently, dosimeters are being used to detect this radiation, and however, the main issue is it collects data for total exposure. So this is not instant and it doesn't give live exposure. So these are some of the requirements that we have decided on to improve lab and human safety while making a practical radiation detection equipment that's immediate and gives accurate feedback. So our requirements are we want to make sure that we can get this detection in 0 to 2 seconds. We want to make sure it can detect radiation at various levels that are similar to the dosimeter. We want to make sure it's less than 3 pounds to, let's say, if you were wearing a lab coat for hours on end and you have 10 pounds extra, that is going to add extra weight as well as impede mobility, and that is another requirement. We want to make sure you are able to be flexible and you can do what you need to do in your job. And we also want to make sure that lifespan and reusability is about 5 years, so that way it's not just a one and done. Next slide, please.
Based off of these requirements, in order to solve the problem, we created 3 designs. The first design is a radiation locating jacket, and what that does, it's a network of fiber optic cables that senses the radiation in different locations throughout the jacket and alerts the user. The second design is actually a bioluminescent reactive glove, and that's a latex glove that has a very specific coating of bacteria that reacts to radiation so the actual user can visualize it. The third and final design is a radiation sensing glove. Similar to the first design, it uses fiber optic cables to better understand the location and intensity of radiation. Next slide, please. And from this, we actually went with the first design. Again, this is a system where fiber optic cables are put into a lab coat, vest, or ESD jacket already used by professionals, and it's able to read in radiation. The components that go into this are fiber optic cables that have doped glass that allow them to read in the radiation. There's a central node in the back where all of the cables meet up and where the data is collected and sent to be processed. There's a processing unit, such as a computer with a special software that actually reads in the data and sends back useful information to the lab coat wearer. And then lastly, there's a screen and user interface, which also has a battery to power the system, and that allows for easier use. Next slide, please. Here's some more actual representations of what it would look like. So on the left, that's actually what it would look like for the user, for example, a lab coat. So you have a screen on the left front pocket, and then it's a lab coat, so you really can't tell the difference. But on the right is showing the network of the fiber optic cables that's built into the actual lab coat, and that's what's able to detect the radiation. And that cross pattern actually allows us to detect the location and intensity of radiation. Next slide, please. And to reiterate, the screen is for the user interface, and it allows the user to see the location on which the lab coat is detecting. There's the radiation rate at which they're getting radiation, and there's the threat so that they can know what to do and next steps to be safe and prepared. Next slide, please.
One of our goals was to keep the cost about the same as or even below the average cost of a personal dosimeter. The most expensive component we wanted to include in our design was the photomultiplier tube, which costs about $200. In the end, we decided to include only one photomultiplier tube so that we could keep the cost reasonable. Overall, the sum of the cost of all the materials, not including the lab coat, comes out to about $306, which is still cheaper than the average cost of a typical dosimeter. Next slide, please. Another important consideration for us was weight. When we were talking to people in industry who would use our wearable radiation detection, they said they wouldn't be able to use it if it was heavy or cumbersome. So for our fiber optic cables, we use polymer because it's flexible and lightweight, so it won't impede mobility or weigh workers down. All the other materials are lightweight as well, so in the end, we only have about a pound of additional weight as compared to an ordinary lab coat. Next slide, please.
So the WRD is integrated into pre-existing lab clothing, which makes it easy to use and easy to remember. Design mobility while retaining accurate and personalized measurement. Extra materials needed to support the WRD will include LabVIEW software for analyzing radiation data on a pre-existing lab computer. Additionally, a battery charge will be needed and hangers to hang the WRD up while not in use will be required. As we showed, our product is lightweight and low cost, making implementation feasible in many laboratories across America. We already have precedent for these systems to be implemented. Fiber optic clothing or the implementation of optic fibers into textiles has already been used and is readily available on the market. They're able to measure data such as health measurements while retaining mobility and easy wearability. Additionally, our radiation detection system has been used in internal use in radiotherapy measurement. And it's been compared to detection devices already on the market, and it has been proven as not only as accurate, but more accurate. Additionally, its accuracy is retained over a wide variety of radiation and for a long period of time without the need for constant calibration. Next slide, please. Our technology, the WRD, is more accurate in timing, location, and detection than other current technology available. It's highly precise in detection down to 5 electron volts, and therefore we can determine a wide range of radiation with high accuracy. Additionally, we provide real-time reading on exposure and hazard level, and we show the location of exposure. These elements are crucial in worker safety so that in the event of a spill or a leak of radiation, workers are able to immediately know how much radiation and where that radiation is so they can get themselves out of that situation into safety quicker. Additionally, in a post-exposure environment, this will provide necessary health information so they know how their health could be affected, and then what steps to take in order to prevent long-term health impacts. The WRD, or wearable radiation detection device, implements accurate and fast and innovative radiation detection, which provides a level of safety for these workers not yet seen in any other technology available today. Next slide.
Thank you very much, WRD. I think you finished just right on time. So now you have 5 minutes for questions.
This is Don. I was wondering, could you mention what type of radiation you're detecting? And then secondly, would it be confined, your detection scheme has you detecting in one of those quadrants you showed? I guess that's a question.
Hi, I can answer the what type of radiation. Sorry about that. So we are primarily focusing on the type of radiation in uranium and plutonium. So gamma, beta, and proton particles specifically. What was the second part of that question? I'm sorry.
How do you triangulate using that network of fibers? How do you find where the radiation's hitting?
Okay, thank you.
I can answer that. So the grid pattern, there's intersection, and you can think of them like little crosshairs or dots. And once the line reads in, so you have an intersection of a vertical and a horizontal line, Once both of those are activated, you can understand the intensity along that point. So you can use almost like triangulation. You have a horizontal and vertical line, and thus you can determine where radiation is strongest and where it's affecting it.
What if you spill something on these lab coats? Are they washable?
Yes, so these lab coats, they have electronic components, but they're interchangeable and removable. That allows it to extend the life, and you can actually clean it just by removing the screen, which you take on and off every time you use it, and the central processing unit in the back.
So you mentioned using a LabVIEW system to process the data. How do you get the data to the LabVIEW system, or is that an onboard processing element?
Yeah, so we have a small processing chip in the actual hardware and the lab coat, and that has a Bluetooth transceiver and receiver, and that's going to communicate with the computer so that the energy draw on the actual lab coat is minimized, so you have a very light and very long-lasting battery, and so that the individual lab coats aren't very expensive, and you export all of the data, it processes it within roughly a second, and then it sends it back to be visualized and be used for the user.
I guess to follow on to Amy's question, would every company that uses this have to require a LabVIEW license as well?
Yes, and so that's the existing solution on the market, is the LabVIEW. Additionally, we could look into the future and possibly having a software where it runs more efficiently and specifically to our product.
Wow, WRD, looks like you've answered all the questions. Good job. Unless there's, I'll pause. You have about another minute for another question, if there is one. If not, we'll dismiss you all and continue on. We'll pause for 1 second to see if there's another question.
Just one quick follow-up to something you said earlier. You mentioned something about the mesh is removed and replaced each time or something like that. Could you clarify that?
Sorry about that. I may have misspoke. The thing that's only being removed every time is you have a little screen that actually fits into your front pocket. And so that allows the user to look at the data that they're receiving, and that's also the battery pack. So you just pick up the battery from the charger, put it in your front pocket, it plugs in, and that allows you to visualize the data. And every time you use it, you put it in, take it out. Otherwise, it's completely the same as wearing a lab coat.
All right, great. I'm glad you were able to find out and offer that clarification. Thank you very much, WRD. Great presentation, and we really appreciate it. And we will move on to the next team as we're getting ready for the next team. The next team is XNET. One of the things that students know is that we have been continuing to work with y'all throughout this entire weekend. And there's been a number of people in the background. I've mentioned the mentors before. We've had just fabulous mentors to be able to come from the Los Alamos Lab organization. And Duncan's been a mentor, but he's also a judge. So he's been playing dual roles. Don's been a mentor and a judge as well. He's been playing dual roles. Adam and Elizabeth, there's been a number of different people who've interacted. We've also had support from the librarians, and the librarians have helped our students do a number of research as well. So there's been a lot of staff that's been going on and working with the students to try to make this event as seamless and smooth as possible. And the students, as you can tell, have spent a great deal of time putting their presentations together and trying to research and make sure that all of the information is put together. And that's what engineering entrepreneurship is really all about. And that is to combine the technical as well as the why, so that you have the opportunity not only to have technology involved, but pay attention to the customers, pay attention to the solution, and pay attention to everything that's going on. Because you can have an iPhone with absolutely outstanding, or any kind of a phone with outstanding technology, but what you're really trying to do is you're trying to share pictures, or you're trying to talk to somebody, or you're trying to connect. And that's the problem that they're solving. So we spent a great deal of time doing that, and our mentors have been just outstanding in helping us do that. All right, we are ready for the next team. The next team is XNET. And as soon as XNET, as soon as you see that your slide is ready to go, you're more than welcome to take over and start your presentation. And we are looking forward to XNET.
Yes. Welcome, ladies and gentlemen. We are Team XNET, or X-ray Nuclear Explosion Tracker. Next slide. I'll introduce the team. You have myself, Ricardo Zardi Prieto, Jessica Virginia Williams, Elias Ramos Ibarra, William N. Garabini III, and Nicholas Pearson. Next.
If fully deployed, the current nuclear arsenal could kill over 3 billion people. To combat such tragic loss, the UN has led the creation of treaties limiting nuclear testing and proliferation. Problem is, there is no enforcement mechanism for these agreements, leaving the whole world vulnerable to hostile actors. When left unmonitored, states with warheads are able to alter the atmosphere by detonating how they please. Furthermore, non-nuclear states are encouraged to develop a nuclear program because they know nobody's watching. Nuclear weapons have claimed thousands of lives already, and ensuring limited testing could stop further death. Even away from inhabited areas, fallout travels widely and can cause life-threatening illness and radiation poisoning across all borders. Given the millions of lives on the line, isn't it time for something better than an outdated system? Enter XNET, the X-ray Nuclear Explosion Tracker. XNET uses innovative technology to not only sense that a nuclear test has occurred, but also where it happened and what fissile material was used. With powerful detection capability and ease of deployment, XNET is the nuclear testing solution. Trust will be renewed, disarmament will continue, and the world will be safe from undetected nuclear threats. Thank you for considering our proposal. And remember, for trust but verify, XNET will satisfy.
Right. The problem we are trying to solve is how to enforce nuclear test ban treaties with a satellite-mounted X-ray detector, because we want to verify that treaties are being upheld and obviously prevent war. Now, next. Now, we know that our requirements are going to be 10 in every direction, less than 50 pounds, less than 20 watts of power consumption. We know that we have to recognize EMP and X-ray signatures from nuclear detonation. We know that we have to do an EMP derived from the instructions, as well as we need to maintain structural integrity during the launch and operation. And now I'll pass it over to Jessica.
Jessica, you're muted.
I am so sorry, y'all. Here's our solution. I am excited to introduce the XNET. It will be mounted to an existing satellite, and so that it will have the electrical and communication component of that, and it is a small box. Next slide, please. Our design has 17.4 watts of power, so just barely within the constraints, 17.4 pounds, which is very low weight to get up into space. It has a 3-sensor packet to measure radio frequencies as well as ionizing radiation. And so these frequencies can be matched to the signature of a nuclear detonation. And that's on the onboard computational module, and then will be reported back to the ground station via the space wire and the communications of the host satellite. Next slide, please. So our 3-detector panel. Our first detector is a scintillator with a cesium iodide crystal and a photomultiplier tube. This will allow us to get directionality as it is shielded except for the scintillator entrance. Our second one is the argon gas tube with a proportional counter. This one allows us to determine the energy, filtering out inappropriate ones that are not of a nuclear detonation. And finally, third, we have a radio frequency receiver, very similar to the pre-existing bang meters. This allows us to determine the signature double wave of the ionization and the stratosphere. Next slide. Here is the radio frequency transmitter. As you can tell, it was attached to the top of it and it has an integrated antenna, so it is outside of the shielding. Next slide. On the inside of the box, we have the PMT module and the gas counter on the other side. And these are shielded. I will pass it off so we can hear more about the project. Next slide.
So we're going to be detecting X-rays and radio waves. For X-rays, we chose to focus on an energy range of 0.04 MeV to about 1 MeV. The reason we chose this range is because this range is perfect for proper gamma spectroscopy, so we can identify the radionuclides of fissile material and their decay products. So for radio waves, we're going to use radio waves to actually measure the changes in total electron current and ionic spheric electron density within our atmosphere. So within a nuclear explosion, it will create a flux of gamma rays. And that flux will those gamma rays will interact via Compton scatter within the atmosphere. And the ejected electrons will actually induce an electric current, which would induce a traveling ionic spheric disturbance. And that disturbance would actually change the electron density and the total electron content. Next slide. So in order to avoid false positives, we need to ensure that our readings are accurate. One way of doing this is that we're going to actually analyze the time difference between measured radio and gamma signals from our satellite. There are 3 peaks that should correspond to measured quantities in both. The first one is prompt gamma emission, the second one is delayed gamma emission, and the third one is actually neutron-induced gamma emission. If for whatever reason, like let's just say the radio signal picks up, but nothing is picking up on the gamma ray detector, then that means that the TID could be not contributed by a nuclear explosion, but by a solar activity or even an earthquake. I'm going to pass it off to William. Next slide.
The XNET device is capable of operating on a satellite in multiple orbits. Geosynchronous orbit is classified as the orbit in which the satellite remains above a fixed point on the equator. And at this altitude, you would need 4 devices in orbit to provide global coverage, and 16 would allow for tracking of the blast point. In geosynchronous orbit, these satellites will also have a much longer life. The sensors are much more capable of working in medium Earth orbit, and it will have a faster response time and can be mounted on GPS satellites, which would allow for blast point tracking as well. This would require more satellites though. Next slide. In order to reach orbit, the satellites are first going to have to survive the rocket launch. Rockets experience about 3 Gs of acceleration on launch and a very, very high vibrational force, which we are going to counteract with aerogel. And it'll be used as a cushion between the delicate parts, such as the scintillator and the gas tube, to dampen the vibration. And the outer structure is made of a strong aluminum alloy that has been proven in spaceflight. And I'm going to hand it off to Nicholas, who's going to talk more about the materials. Next slide.
All right, so a deeper look into materials. So for our exterior, we use an aluminum coated polyimide. And what this accomplishes is it reflects solar radiation and maintains internal temperature for the inside of the instrument for the internal circuits top rate, which also provides a layer of defense against dust impacts as well as space debris. And it would be around 2 millimeters thick. The aluminum type we used for the inside of the instrument would be an aluminum lithium alloy 2195. And this has high strength as well as lightweight properties. And it's fracture resistant at cryogenic temperatures, which exist in space. And we also included a photoelectric anodization for aluminum to prevent bonding and interaction of metals inside of the instrument. And as Will mentioned, we're going to be using silica aerogel to absorb shock and the initial launch. And then we also consider vapor deposited gold taping for protection of the integrated circuits. Next slide, please. So what's so innovative about our product? So what our product accomplishes is it integrates multiple sensors into one complete instrument and is compatible with multiple orbits with the type of materials that we used. It also accomplishes detection of nuclear explosions, not only in the atmosphere, but as well as underground and in space. and we used only about 35% of the constraint weight that was allocated to us. Next slide. And next slide, please. And that's it. Thank you.
Thank you very much. I appreciate it. All right, judges, you have 5 minutes for questions.
This is Don. I really didn't see an analysis of alternatives. Can you talk to that a little bit?
Oh, absolutely. We definitely considered a lot of alternatives, but most of those were integrated into the final solution. I know one of the prior teams was talking about using a germanium or a silicon semiconductor. However, we decided against that because they are untenable in space and would have a shorter lifespan. So for cost efficiency, we decided to go for the gas tube and the radio. And some of our alternatives were just a gas tube. And we eventually decided to integrate that into the final product by using a proportional counter, because that allows us to determine the energy content of the radiation, allowing us to determine possibly even what type of fissile material was used, if it was a uranium waveform versus a plutonium waveform.
Curious, the scintillation tube that you chose were you able to choose the dimensions that you wanted for one of those, or were you forced to find a solution based on the design restraints for the scintillation tube?
So we found one like already in production by a company that fit the specifications we need, and then made sure that it was, you know, the right size to fit into the design.
What was the overall size of it, like length of it, do you know? Or
I happen to know because I looked at the spec sheet for it. It was about 1 inch in diameter by 2 inches long, and it was perfectly capable. And then that was just the photomultiplier tube. So we do have an external scintillation component that just sits right in front of it.
Did you
How
have
are you
a
going to test
design
it this?
for the sensor?
Sorry, could you repeat that?
Did you have a design life for the sensor? Oops. No, I mean,
I'm sorry, what did you ask? A design line?
a design life.
How long will the
Oh,
design
how long does
last?
it have to last?
Okay. We were thinking of about 5 to 10 years because that's the average lifespan of a mid-Earth orbit satellite. If it was in GEO, it could possibly do more. And that's one of the reasons we decided to include 3 sensors, was that even if one of them went out, the other 2 would still have the capabilities.
How will you test the system to make sure it's working in the absence of a nuclear explosion?
I think if it was in that scenario, then that means it would still be here on Earth, and we would just expose the scintillator to a certain range. We would expose it to a uranium source, like let's just say uranium-235 or something like that, even though I don't think we'll be able to get that. And then it will undergo some form of gamma emission, and it should be able to detect it. And then for radio waves, we have a slide. I was hoping, can you go to the person who's controlling the slides? We have a bunch.
Was it either 26 or 27?
Imagine.
No, it was that one.
Are you talking about 25?
No, I can't find it. But yeah, that's how we would test the design.
So just to clarify, you know, once it's in space, it may be years that go by with no explosion on Earth. How do you make sure your system is still working once it's in space?
Well, of course, there's background radiation. So most of the components will pick that up to some extent because not all of it will be filtered out. And the radio detector is designed to detect the traveling ionospheric disturbances. So those can be caused by a variety of things, gamma ray bursts, so it should be detecting it at some point individually. But we differentiate that from false positives by the combination of the two X-ray detectors and the radio detectors. If not all three of them go off, then we know that it is not a nuclear detonation. So the false positives actually serve as the testing of each individual component, just not all three at the same time.
So do you have your system relaying that data back to somebody on Earth, or is it just sort of an alert that something happened that you would relay? How would you decide what information you relay and how often?
We're only looking for disturbances within the ionosphere, and that's actually been characterized, and the information is actually updated continuously by the GPS system that we have all around the world, and so we can compare it one another. And also, the sensor goes on top of the host satellite, and ideally, the host satellite would be one that would be interested in doing that, relaying back the information.
Okay, you have time for one more quick question.
So I'll ask one last one. So a lot of times with space instrumentation, you're really concerned about dissipating heat. But in your case, it actually looked like the opposite. It looked like you were trying to keep heat in to keep the thing working properly. Is there an issue of where you would get to the point where you have to dissipate heat in order to keep the sensor working properly?
So I can go ahead and answer that question. So our understanding was that in the need of dissipating heat, it would be dissipated downwards through the metal plates into the base plate of the satellite, because we were told that that heat could be emitted into that to get rid of it.
Okay.
All right, thank you so much, XNET. We appreciate the presentation and appreciate the information. Judges, thank you very much. And judges will again give you a few minutes to be able to complete your scoring and to be able to submit those scores. As we're getting ready for Shockwaves, which should be a very explosive presentation. Sorry about that pun, guys, but nonetheless, Shockwaves will be getting ready and we'll be putting those together. I again want to continue to thank everybody that's been engaged throughout the entire weekend. And students, we want to thank you primarily. There's been 3 of our staff engaged. It's been Don Bailey and Jim Donnell and Aaron Williams. And we've all been engaged and involved with you throughout the entire weekend. We've enjoyed working with each and every one of you and working with the teams. It's a pleasure to be able to do these things. Not without, and what we like to see is we like to see you continue on. We'd like to see you to take this information and the experience that you've had, share it with others, but also take it into your classes, take the presentation skills, take the analysis, take the working with mentors, taking with all of these skills that you've learned and practiced throughout this weekend, and particularly take the skill of innovation that you have practiced throughout the weekend. And that is that you know now that innovation can happen in a very short and intense period of time. And that's the skill that we want you to develop and continue to foster that throughout your college as well as your career throughout the rest of your career. So take this with you. We're here always to help you at any point in time. If we can ever help you in any way, please be sure to contact us. All right, we are ready for Shockwave. And Chuck, if you wouldn't mind turning off your video. And Shockwave, when you see your slide shared and ready to go, then y'all are more than welcome to start your presentation.
You can go ahead and start the video. We'll wait a minute. The next slide.
Whoa! Oh! Oh my God, there's pieces of debris falling all around us.
Demolition disaster. A man seriously hurt when debris from a condo building goes flying.
It's obviously substantial explosions sending both smoke and shrapnel into the air.
order to create safer and more controlled explosions, we created an array of sensors that can detect the force of fragment impacts. The sensors will help us to better understand the spread of shrapnel and how we can modify current explosives to produce less lethal shrapnel patterns. With this information, we will be able to create better explosion models, making it safer for workers in demolition as well as everyday civilians.
Good afternoon. If you can go to the next slide. My name is Aaron Kendall. I'm a junior level nuclear engineer. Excuse me, the previous slide. I spoke too soon.
Howdy, I'm Nomar LeBron. I'm a sophomore general engineer major.
Howdy, my name is Vishal Saini, and I'm a marine engineering major.
Howdy, my name is Nick Vasquez. I'm a multidisciplinary engineering technology major, and I'm also a sophomore.
Howdy, my name is Yuandong Wang, and I'm a freshman in general engineering.
If you can go to the next slide, please. So what we found through our research into the topic at hand is that there needs to be a better understanding into the fragmentation of explosive devices and the current systems in place to do so aren't quite adequate. If you can go to the next slide. So this is our need statement. It mainly, from what it seems to be saying, is it's telling us that we need to design a device to stick within a 3 centimeter space between 2 foam pads. It's going to be able to detect fragmentation impacts of as small as 30 grams, and they must as well be able to be networked together in order to average impact loading values over an area that's going to be interacting with some fragmentation. And they must also have low power consumption and be able to wirelessly transmit data. If you can go to the next slide. And again, from this need statement, we drew out 5 requirements that we must meet. That the device must fit within a 3 centimeter boundary between 2 foam pads, be able to detect small particles that might be impacting it, and be physically networked together, to cover a surface area of half a square meter so that there's no spaces in between. Use a low voltage amount for the total device, each individual device, and be able to transmit data wirelessly so as you can get it away from wherever a blast may be occurring. On the next slide. From the research that we have done, we found that there are already several different ways that people try and calculate the trajectories of fragmentation from explosions. Some of the ones that I have seen they've gone from everything from Monte Carlo probability simulations to high-speed cameras in conjunction with X-ray footage. Each one of these has their own drawbacks. The high-speed footage and the X-ray can become obscured by other objects that might be interfering in the way. And the video, of course, can or will have trouble encountering and seeing things through large flashes of light, debris, and smoke, and whatever else is associated with the explosion. Next slide.
Yes, so we have 3 solutions considered. The first one is a fabric with sew-in sensors wired to a transmitter. This design is not modular, however, it is low on complexity. The second one is an array of sensors and Arduinos wired to a single transmitter. This design is modular and is low on complexity. The third one is an array of sensors communicating wirelessly with each other. This is modular. Structurally, it will be high on complexity. However, because of the way it's designed, it's not as prone to system failure. Next slide, please. So you can see here on the top, we have 2 drawings of our electronic assembly. On the top, you can see an Arduino Mini working with an HM10 Arduino Bluetooth module, both mounted. In the middle here, in the gray section, we have an electronic container acting as protection. On the other side is our sensor. On the bottom, you can see a wiring diagram in here. Next slide, I'll hand over to Nomar.
After considering those previous prototypes, we finalized our product with the following specifications. So the overall dimensions were 5.8 centimeters by 5.8 centimeters, which is actually just the total size of our FlexiForce A502 sensor. And the total width came out to be 2.25 centimeters, well inside of our 3 centimeter requirement. A unit price for one of these would be estimated $60 based on the market value for each component, each individual component. Both the Arduino and the HM10 are going to be taking 3.3 volts from an external battery source. The sensor has a response time of less than 5 microseconds, making it a very precise and very high sensitivity sensor. And the Bluetooth has a range of 100 meters, allowing for a greater distance between the data receiver and the actual explosion. Next slide.
Here you see us demonstrating our prototype. The plexiglass plate and button you see is a stand-in sensor. This stand-in sensor will only allow us to determine whether a force is being applied or not. When we are able to implement the FlexiForce sensor, we will be able to determine the force magnitudes in order to have useful data collection. Next slide, please. Here we are demonstrating our data transmitter wireless network. Here we are demonstrating our data transmitter. All other modules will transmit their data to this module via a wired connection, and this module will then take that data and transmit it via a wireless Bluetooth connection to our data receiver. Next slide.
Here we are demonstrating the physical connection between the two sensors. In our prototype, we just have one wire connecting the two, but in our idealized model, we plan to have 4 wires coming out, one out of each side, in order to be able to stack the sensors in sort of a grid-like fashion in order to make the surface area as large as we need to. Next slide.
There are multiple fields that can use our design. First and foremost, it will be our U.S. military. As we know, the military goes on operations for recon all around the world, and they encounter landmines and other explosives and objects. So they can definitely use our products to measure how shrapnel goes in different directions, what types of materials and what the G-forces are on those. So we can definitely use it more for military refinement. Another field is for mining operations. Miners use it to create new digging sites, and sometimes things can go wrong and personnel can be hurt by these explosions. They can use our device to better test how to set these explosives. Third would be a controlled demolition. Say you're in a crowded city and there is an old structure that you want to take down. You need to make sure you do it properly so you can avoid damaging other property around, which can result in a huge lawsuit or injuring any other people that may be in the area. Next slide, please. What makes our product unique from the others is the way that it's designed to capture the explosion from all sides. If you look at ballistics testing, it only occurs in one direction. There will be a bullet that'll go to a site straight ahead, and they use their audio sensors and optical sensors. An issue is with explosions, you can't use an optical sensor. Sometimes the light will blind you, it'll blind the camera, and it cannot detect those little particles that are suspended in the air. So ours will be able to capture it from every single side instead of just one. And it's based more off of feel, and the piezoelectric sensor will pick that up. Next slide, please. So if we can carry this project forward, there are some alterations that we can make. We can change the foam material based upon the blast radius and the size of the shrapnel. The material that's used, it could be metal, it could be rock, it could be plastic, and the amount of heat that occurs during the explosion. It could be a smaller explosion that sends shrapnel farther away, or it could be a large one.
And Shockwave, thank you very much. That was your 10 minutes. And now I'll open the floor for the judges to be able to ask questions. Judges, you'll have 5 minutes to ask questions of Shockwave.
This is Don. Nice talk, team. Can your sensor also detect the mass of the frag as well?
I believe in order to do that, it would have to be taken in conjunction with any high-speed film technology that might you'd have to take into consideration the size. So it'll take up the magnitude of the force that was applied to it, and then you might be able to tie that in with some photographs you have. Not this particular device, no.
This is Edgar. So before the fragment gets to the sensor, there's going to be a large pressure spike from the shockwave. Is your sensor able to withstand those initial pressure spikes in order to record a fragment impact, or even be able to differentiate between the two?
In the current setup, I do not believe it is. If you were going to do something like that, you would have to run multiple tests without fragmentation in the first instance to see what kind of baseline you could get on the impacts from the blast wave. And then after that initial impact, you would then run it with fragmentation to maybe see how you would, what kind of magnitude of force those would be generating on those pads.
This is Duncan. If one of your sensor elements is destroyed, does the system stop working as a whole, or is it resilient to the destruction of one component?
Yes, a component that is damaged will send its last received measurement, and we can rely on the data of the other sensors that are nearby, and they'll send the information that they gather. But our devices are set up where you have to judge what kind of environment the explosion will be in, and then adjust it to that to make sure the materials that you're using don't get damaged.
How scalable is your system to a larger array of sensors?
I don't see why, given it correct voltage input and power source, why we could not scale this up to as large as we wanted.
So what would be the number of sensors you would think would be necessary for a typical application?
We know for an application of 0.5 meters squared, we will need roughly 10 sensors.
So you'd scale that up to whatever surface area you needed to cover, and then maybe see how it might be influenced by shrapnel.
Okay.
How does that granularity of data fit with the size of the shrapnel that you're trying to measure?
I don't quite
It'll
understand the
measure
question.
the G-forces that are felt on the pad, and using an additional sensor that can measure velocity, you can determine the size of the shrapnel.
How does the density of your sensor network correspond to the number of pieces of shrapnel that your application might have, or the size of the shrapnel, or the shrapnel field that might be hitting your sensors?
I'm sorry, can you repeat that question?
So when you have your sensors, right? You have your array of 10 sensors, but it's going to be hit by a set of shrapnel, right?
Mm-hmm.
So how does that density of sensors that you have in your sensor network pick up that entire set of shrapnel?
So each sensor is supposed to detect whatever collisions it has in milliseconds, and it is wirelessly transferring it to a communications base. So it'll be data logging in a computer. So you'll know which sensor picked it up in which milliseconds. And you can go and look at which sensor displayed what impact at what time. So you can get all of those measurements that are surrounding it.
So I would think to provide useful information, you would have to have the energy level associated, and some other people have asked questions related to this, rather than just the acceleration level of the piece of the fragment. You know, particularly if you're trying to look at, you know, how damaging is that piece of that fragment going to be to whatever structure you're going to put the sensors on. Did you talk at all about, and this then gets back to, can you have a mass measurement along with the acceleration measurement? But at the end of the day, would just the acceleration measurement alone give you adequate information about how damaging the fragment would be?
I think our idea was through calibration, we could then determine, after having calibrated it to different known explosions with known forces, that we could determine the masses afterwards.
Okay.
Okay, and thank you very much. That's all the time that we have for questions. Thank you very much, Shockwave. All right, now it comes the real difficult time for the judges in trying to determine their scores. It is right at 4 o'clock, or maybe a minute or so past 4 o'clock. We're going to take a break until 4:10, and at 4:10 we'll get back together and we should be able to announce the results of the scoring and results of the team competition. So we look forward to seeing you back at 4:10. Thank you very much. The winners, as we announce them, thank you very much, judges. I could tell it was a struggle. You all were all having such tremendous difficulty in trying to figure out how to score this, but I really appreciate everybody's activity, and you really did a great job putting things together. So thank you very much for all your activity and effort. So without further ado, let me announce the third place winner. And the third place winning, the students, your team will receive $500, and we will be placing this in your student accounts as scholarships. You should see it in the next few days, and we'll put this in your team accounts. And the third place winner is TKO Nukes. So if you would turn on your screen, we would like to congratulate you and thank you very much. Y'all did a great job, wonderful job. So that was third place. And if I could figure out how to do the cheering mechanism, I'd figure I'd be able to play a cheer. But I can't get the cheer going. So anyway, so congratulations. Thank you very much for everything that you've done. And again, if you're interested, let us help you continue on. All right, TKO Nukes, if you will turn off your videos, we're going to go on now to the second place team. All right, again, judges, thank you so much for all that you have done and how you have helped out the teams. It's really been tremendous to see you. And thank you for giving up your Sunday afternoons. The students have really given a tremendous amount throughout the weekend and participated fully. I know one of the teams was here until 2:30 or 3 o'clock this morning. I wasn't here. We were winding up. I was winding up sleeping. That was one of the questions we asked them last night. Was they're going to be able to have any kind of sleep? And all of them assured us that they were going to get some sleep. So we certainly hope that they did. All right. Without further ado, let me announce the second place team. And the second place team is Shockwave. So if you will come on and tell us, again, let us congratulate you. So congratulations, Shockwaves. The Shockwaves will receive $750. And again, we'll be placing those in your student accounts. If you would like to later on, be more than happy to take a screenshot. Let me just grab something here and I'll get a quick screenshot of everybody so that we have that available. And everybody say cheese and ready. And here we go. All right, we got that screenshot. So now we've got it all. All right, congratulations, Shockwaves. And again, I'll let you turn off your video so that we'll get on to the first place team. So I know students, you spent a lot of time this weekend and everybody did, and all of us are going to be back hard at it again tomorrow morning, and you'll be catching up on your homework and catching up on all of the different jobs. But I really, again, judges and mentors, I cannot tell you how tremendously helpful you have been throughout this entire weekend and how much we appreciate all of your effort. We genuinely could not do this without you. So for the first place team, let me congratulate the first place team, and it is XNET. And XNET, if you would come on and be able to tell us congratulations, and congratulations to y'all. You did a great job, a nice briefing. I love your the background and the animation and all of that. It's really very well done. So XNET, y'all will be receiving $1,000 for your team. And again, we'll be placing this in your student accounts. Congratulations and thank you. Stay on. Let me get a quick screenshot of y'all as well. And that way we have an opportunity to get that. All right, here we go. 1, 2, 1, 2, 3, a screenshot. Perfect. Thank you so much. All right, we've got that going. All right, well, this concludes the Aggies event. Judges, mentors, students, thank you so much for everything that you have done for this Aggies event. Again, we want you to take forward and continue to go on and continue to develop your products. Please let us help you in some way. And also, I know the Los Alamos Labs organization would like us to remind you of internships that they have available. We'll be contacting you with additional information, and that way you have an opportunity to connect with them and continue helping us protect our nation and to work with the jobs that they are doing. Thank you again. And again, Don and Duncan and Diane and everybody here, thank you so much for everything that y'all have done. And we look forward to continuing our cooperation. Thank y'all.
Thanks, Rodney.
You bet. Have a great rest of the day.
Okay.
Bye-bye.